Hi, welcome back. In the previous lesson on cryptography, we looked at some of the classical symmetric ciphers, and we ended up seeing that they all suffer from a problem, namely the key exchange problem. The need to be able to exchange keys between Alice and Bob in order to perform encryption and decryption. In this lesson, we're going to look at some of the modern cryptographic techniques that are used to solve this problem, which is an important problem because if you can't solve this problem, you can't really have a secure internet where we can make secure banking and credit card transactions. So the key exchange problem is the problem common to all symmetric key ciphers, namely how can Alice and Bob share a secret key without Eve getting it? The implications of this for the internet are enormous. You wouldn't be able to do banking and credit card transactions unless you were able to have encrypted communication between client and servers. For this, they need to share an encryption key. The first solution that was used to solve the key exchange problem is known as the Diffie-hellman key exchange algorithm. The idea behind it is to divide the key into two parts, a public part that is shared and a private part that's kept secret. This video by Britt Cruz is one of many that he's produced to explain cryptography. It gives a nice analogy of the Diffie-hellman key exchange using paint.
Imagine two people who have never met could do an amazing trick. Alice and Bob are allowed to communicate over a line which is tapped, so any message they pass will be intercepted by Eve, who is always listening. The trick is to agree on a secret numerical key, without Eve also obtaining a copy. How is this possible? First, let's explore how this trick is done using colors. So how could Alice and Bob agree on a secret color without Eve finding it out? The trick is based on two facts. One, it's easy to mix two colors together to make a third color. And two, given a mixed color, it's hard to reverse it in order to find the exact original colors. This is the basis for a lock, easy in one direction, hard in the reverse direction. This is known as a one-way function. Now, the solution works as follows. First, they publicly agree on a starting color, say yellow. Next, Alice and Bob both randomly select private colors and mix them into the public yellow in order to disguise their private color. Now, Alice keeps her private color and sends her mixture to Bob, and Bob keeps his private color and sends his mixture to Alice. Now the heart of the trick. Alice and Bob add their private colors to the other person's mixture and arrive at a shared secret color. Notice how Eve is unable to determine this color since she needs one of the private colors to do so. And that is the trick.
That's a great analogy of the one-way function and the Diffie-hellman key exchange algorithm. Here's an app that you can try to play with color mixing analogy. In this case, however, the colors are represented by a 6-digit hexadecimal value, an RGB value, which is the standard way colors are represented in browser languages such as hypertext markup languages. The first 2 digits represent the amount of red, the second 2 digits the amount of green, and the third 2 digits the amount of blue. Give it a try. You pick a secret color by inputting its hexadecimal value and a shared color, and then click on Show Shared Secret to observe the secret that would be exchanged with the app.